Hello, we will start now a part of the course which is related to, is actually a seminar, which is related to the description of a methodology of thermo-economic analysis, which is called thermo-economic functional analysis, which is a procedure to make the thermo-economic analysis of energy system, which I consider more complete compared to the others, because it takes into account also especially the role of the dissipative components into the economic balance of energy systems, and especially it opens the way to the consideration of the role of the environment into the operation of energy system, the consideration of the role of the environment from the economic point of view. I will make a description of this thermo-economic functional analysis starting from the, I can say, usual methodology in order to develop a thermo-economic analysis, which is the theory of exergetic cost. So we start from the theory of the exergetic cost, and starting with this, I can show you better the differences that there are with the thermo-economic functional analysis. So the outline of this seminar are that I will start with notes of thermo-economic functional analysis. It will be a long part related also to the reminder of the theory of the exergetic cost, as I said. And after, I will move to an example. As usual in our course, the example will be done with a simple type of plant, which is a gas turbine with air preheating and in CHP configuration. So you can making use always of the same example to see how the different methodology can be applied to the same energy system. After, of course, we will move again to a more complex system, which will be a combined cycle, but the seminar will deal only with the gas turbine. So I start with some remind of the classical theory of the exergetic cost, which is, I can say, the most used procedure in order to make a thermo-economic analysis of an energy system. So, as you see in the slide, we can consider a component of an energy system. You can say a single component. You have a complex energy system composed of several components, but let's consider just only one component. This can be a heat exchanger, can be a compressor, can be an expander, can be a chemical reactor, and other components, but it is only one. So this component has an input in terms of exergy, which is a fuel. So exergy we can flow, which is the fuel of this component. It has an output in terms of exergy, which is, as we discussed in the course, the product is called the product. So the aim in terms of exergy transformation of this component, the real aim is to produce this flow of product. So Psi is the product of the component, and in between the two, the fuel and the product, there is the destruction of exergy in form of irreversibility, Psi. So Psi, we said, is the product exergy flow. But now we can make a step forward. We can define a concept which is called the exergetic cost of this exergy flow. So the exergetic cost of the exergy flow Psi Pi is named Psi star Pi. This exergetic cost is defined as the exergy flow which is necessary to be spent in order to obtain the flow Psi Pi in the exit of this component. So in this simple analysis, in this simple example, the exergy which is necessary to spend in order to obtain a product Psi Pi at the outlet of this component is, of course, the exergy flow of the fuel Psi Fi. So as I wrote, so this exergy flow which is necessary to produce the flow Psi Pi is equal to the exergy flow of the fuel of the component Psi Fi. So at the end we can say that the exergetic cost of the flow Psi Pi, so the symbol psi star pi is finally equal to the exergy flow of the fuel of the component psi fi. If still in the same component we consider the inlet flow psi fi, this comes we can say from the external of the part of the system. So it is not produced by the component, it arrives from the external environment. So in case of an external fuel, the exergy that has to be spent in order to obtain the psi fi flow is equal to the psi fi flow itself. So at the end, the exergetic cost psi star fi of the flow psi fi is equivalent to the exergy flow psi fi itself. So in the case of a fuel, of a component which is alone, the exergetic cost of the fuel is equal to its exergy content. Moving on, we can see that some interesting effect. If we consider the exergy balance in the component, we see that the fuel psi fi is converted partially in the product psi pi, and partially is destroyed in form of irreversibility psi I. So, because of the balance, we see that the exergy flow of the fuel psi fi is higher, or in the extreme cases, equal to the exergy flow of the product psi pi. The equality is only right in the case in which the irreversibility is equal to 0, which is, of course, the case of a reversibility operation, which is an ideal case. So in general, psi fi is higher than psi pi. So because the exergetic cost of the flow pi is named psi star pi is equal to the exergy flow of the fuel psi fi, as we said in the previous slide, we can conclude that the exergetic cost of the product pi, which is psi star pi, is always higher, or in the extreme case, ideal case, equal to the exergy flow of the itself of the product psi pi. So the exergetic cost is higher than the exergy content of a flow. Following this, it is possible to define the concept of a specific exergetic cost. So to normalize, we can normalize the exergetic cost towards the exergy flow of the stream that we are considering. So normalizing, we obtain the concept of unit exergetic cost. The unit exergetic cost of the considered exergy flow is defined as K star pi, and it is equal to the exergetic cost of the flow psi star pi divided the exergy content of the flow itself, which is psi pi. Because, as you remember, the exergetic cost psi star pi is higher than the exergy flow psi pi, it means the unit exergetic cost K star pi of a product flow, of a flow product of a component, is higher than 1. So it increases. In the simple case of only one component that we are dealing now, you see that K star pi can be written in the following way. The psi star pi, you remember in the previous slide, or even here in the top, is equal to the exergy flow of the fuel, so psi fi. So we put into ratio psi fi with psi pi, and it is nothing else than the reciprocal value of the exergy efficiency of the component. So you see the K star pi, the unit exergetic cost of the product of the fuel, of the product of the component, increase as much as the exergetic efficiency of the component decrease. So the cost increase when the exergetic efficiency of the component, the cost of the product in terms of unit exergetic cost, increases as far as the exergetic efficiency of the component decreases. We have to generalize it, moving from one single component to a global system. So if we consider a complete system, the complete system has E external fuels So a fuel of methane, a fuel of solar irradiance, a fuel in terms of chemical, and U product, so let's say electric power, heat recovered from in a CHP application, another form of chemical. So some external fuel E and some external product and some product U. The exergy balance becomes the following. The sum of the exergy flow of the fuel, of the E fuel Psi minus the sum of the exergy flow of the product U product Psi, they are equal to the exergy destroyed by irreversibility inside the global system. So this is a simple exergetic balance. If we write the exergetic cost balance, so if we move from the balance of the exergy flow to the balance of the exergetic cost, the balance becomes the following. Because Psi, the irreversibility flow, has not an exergetic cost associated, the balance becomes the sum of the E exergetic cost Psi star I minus the sum of the, in the product, U exergetic cost of the product Psi star J, sum up to 0. So it means that while the exergy flow are not conserved in the system, because part of the inlet exergy flow are destroyed by irreversibility, at the contrary, the exergetic costs, so the costs associated to this exergy flow, are conserved inside the system. So the sum of the exergetic cost of the inlet fuel is conserved in the sum of the exergetic cost of the outlet product. So their balance is equal to 0. So the exergy is not conservative, the exergetic cost is conservative. Now we have to generalize in a way in order to write in a more compact mathematical form all these balances. So considering a system which has n components, heat exchanger, compressor, chemical reactor, and so on, and m flow of exergy connecting the different components, of course n, the number of components, and m, the number of exergy flow, is usually different. The exergy and exergetic cost balances in the global energy system can be written in the following way. We can write for every single component, for each single component of the system, a balance of exergy, as we have done in the beginning of this lecture. So the sum of Psi j multiplied by index Aij is equal finally to the irreversibility produced in the component, so the exergy destroyed by irreversibility into the component. We can write this equation for every single n component of the plant, of the complete system. So for each I going from 1 to n, where n is the total number of components of the system. So this is a way to write the same equation that we have already seen in a more compact way, because the Aij index is simply an index that expresses if the exergy flow is an inlet in the component, an outlet in the component, or simply this exergy flow doesn't belong to the component that we are studying. So Aij is equal to +1 if the J flow is an inlet flow for the component I. Aij is equal to -1 if the J flow is an outlet flow for the component I. Aij is simply equal to 0, so it doesn't exist if the J flow is not connected at all to the component I. So you see, if we put in a matrix form all these n balances equation, we can obtain this form of matrix equation at the bottom. So the same balance can be expressed in a matrix form introducing a matrix A, which has n rows, which are the number of components, so because the balance is component by component, and m column, because the other variable that we are considering are the m exergy flow of the system, containing the parameter aij with the defined signs, which represent, this matrix at the end represent the topological description of the system. So it represents how the system is organized in terms of which flow enter in which component. Takes a +1 if the flow j enters in the component I, a -1 if the flow j exits from the component I, or 0 if the flow j is not connected to the component I. So this equation can become, this sum of this series of equation can become this form, in form of matrix, the matrix, topological matrix A by the vector of the variable which are the flow of exergy is equal to the vector of the exergy destroyed by irreversibility in every single component. So this is the topological equation in order to be that allows us to calculate the exergy flow of all the flow of the all the energy flow included in the system. As we have done, we can write the same in form of not exergy flow but exergetic cost. So we can write exactly the same balances, but remember that the exergetic cost of the irreversibility, so of the psi, is equal to 0. So the same balance in terms of exergetic cost can be written in the following way: sum over the m flow of aij psi star j equal to 0. And this can be written for all the n components of the plant. So again, at the bottom, we obtain the total equation extended to all the components of the system, which is written in matrix form. Again, there is the topological matrix A, which contains the various parameter aij, multiplying the vector of the exergetic cost of the exergy flow of the system, so psi star. This is equal to 0. But you notice the topological matrix is of course the same. So in the first form we calculated the psi, the exergy flow. In the second form we calculate the exergetic cost of every single exergy flow. In terms of matrix equation, you can understand that usually the number of flow m in a system is higher than the number of components n in the system. So where you have more flow than components. So m is higher than n. So in order to solve the matrix equation, you need to add some auxiliary equation to the exergetic cost balance of the component in order to solve the system, because otherwise the system cannot be closed mathematically. So you have to add m minus n auxiliary equation to the system of equation. So this m minus n auxiliary equation can be written in the following way. We are considering now the equation for the exergetic cost. So the auxiliary equations are written as alpha, matrix alpha by a vector of variable psi star equal to a vector of, I can say, known values, already known values, which are the value of the external evaluation given to some of the flow of the system, which is a vector omega. So omega is the vector of the external evaluation. So if we put all together the first matrix A and the second matrix alpha, the merge of the balance of auxiliary equation produced, the merge of the balance component by component and auxiliary equation produces the following matrix equation. So A submatrix A over submatrix alpha multiplied by the vector of the exergetic cost is equal to submatrix 0 over the submatrix vector 0 over the subvector omega. This is the total equation which is can be used to evaluate the exergetic cost of all the exergy flow of the system. Now the point is how to define the exergy auxiliary equation alpha psi star equal to omega. To do this, we can use some rules given by the professor that have invented and formalized the theory of the exergetic cost. So, you see the auxiliary equation suggested by Valero in the paper of Lozano and Valero of 1993 are based on a series of very simple rules. So following this rule, you can write in your system all the auxiliary equations that are needed in order to have the part alpha by psi star equal to omega. The first rule is the exergetic cost of exergy flow coming from the external environment, and I say not from a component of the system, so from the external environment compared to the system, is equal to the exergy content of the flow itself. What we said at the beginning, if exergy flow comes from the external environment, its exergetic cost is equal to the exergy flow itself. So this adds a number of equations equal to the inlet flow into the system, from the external environment into the system. So we have that in this equation Aij psi star j equal to omega j, Aij is equal to +1 because they are entering, and omega j, you remember, is equal to the exergy flow psi j itself. So what we are writing is that the exergy cost of a flow coming from the external environment is equal to the exergy flow itself. Psi star j is equal to psi j. The second rule, you see, if in a component the fuel is defined as the difference between the exergy content of the inlet and of the outlet flow, so it happens, imagine a heat exchanger, a hot fluid in the heat exchanger, in which the fuel of this heat exchanger is the difference between the inlet exergy of the hot fluid minus the outlet exergy of the hot fluid. So this difference is the fuel. So if it is the case, the two flows, so inlet exergy of the hot fluid and outlet exergy of the hot fluid, the two flows assume the same unit exergetic cost. So this adds a series of other equations to the system. Rules number 3, if a component has a total product composed by more than one exergy flow, so in a system you have more than one exergy product, they all assume the same unit exergetic cost. This adds other equation to the system. Rule number 4, if there are exergy losses from the system to the external environment, so flow which are losses and not really product, is important. In absence of an economic value, so if we as an analyst doesn't give to this flow a economic value, we can say that this flow assume a unit exergetic cost which is equal to 0. They don't have a exergetic value. So this adds another series of equation, auxiliary equation. So these rules add the number of equations needed to solve the matrix problem. So I stop here the part 3.1, and we will now move to the continuation in the part 3.2.